Starting a new chapter here, first section of chapter 6, which is angles of polygons. Okay, first we need to talk about what a polygon is. Okay, a polygon's a closed figure with a finite number of sides. Now, what's it mean to be closed, first of all? Okay, is a closed figure. That is a closed. That is a closed figure. That is not a closed figure. Okay, this would be a polygon. This is not a polygon. Not a closed figure. Has a finite number of sides. A circle is not a polygon because it does not have a finite number of sides. Okay, and then we classify polygons by if they're convex or concave. Remember, we talked about this a little bit a long time ago. If it's convex or concave, the test you can tell. Does anybody remember how you can tell? I mean, you can tell a lot of times by just looking at it, but when you get a big figure, it might be difficult. Anybody remember the test we can do to tell if it's convex or concave? If you extend one of the sides, or any of the sides, of the polygon, if it doesn't go through the interior, it's convex. Meaning in that right figure, I just extended every one of the sides, and none of them went through the interior of the figure. Therefore, it's convex. Whereas concave, if you extend any of the sides, or in this case I haven't yet, but this one, I extended this side, it goes through the interior. It is concave. Okay? So we classify polygons two different ways, whether they're concave or convex. If we extend the sides and it goes through the interior, it's concave. If it does not go through the interior, it's convex. We're going to be talking right now a lot about convex polygons, okay, and certain properties that they have. Just convex for today. Okay. This is not something you need to write down, but I want you to have seen it. So don't worry about writing this down because you won't be tested over this. But you will need to probably know the first at least 6 or 7, if not most of these. Now, how we name polygons is by their number of sides. Okay? And we have specific names for polygons with 3 to 10 sides and then 12 sides. Okay? We know a 3-sided polygon is a triangle, a 4-sided figure is a quadrilateral, 5 is pentagon, 6 is hexagon, 7 hept, 8 is octagon, 9 nonagon, 10 decagon, and 12 is dodecagon. For 11, there is no side that we use. And for anything over 12, which includes 11, we call it just the number of side gon. I mean, if I gave you an 18-sided figure, it would be called an 18-gon. If I gave you a 200-sided figure, it would be called a 200-gon. Okay. You won't be tested over this specifically, but I would like you to know if I give you a hexagon, then it's a 6-sided figure. A pentagon is 5. Okay. And anything 11 or over 12 is called a 15-gon or a 20-gon, or however many sides it has. Okay. Or a 21-gon. Correct. Very good. Yes. We're talking about interior angles of polygons, okay, and what they add up to be. So this is the first theorem on your postulate sheet. You don't necessarily need to write this down because you get to use this. Okay. It's called the interior angle sum theorem. And that theorem, and I'll write a little bit bigger here, is that S is equal to 180 times the quantity n minus 2 in parentheses. Now, what n stands for is the number of sides of the polygon. If it's a 20-sided figure, 20 would go in place of n. What S stands for is the sum of all the measures of the interior angles, which means in this figure, this is a what gon? Or what is? It's pentagon because it's a 5-sided figure. The S stands for all the interior angles added together. Okay, so this stands for what all the angles on the inside add up to be. That's what S stands for. Okay, S is the sum of all the interior angles. N is the number of sides of the figure. Sometimes I might give you this. Sometimes I might give you this, and you have to find the other one and just work the algebra from there. Okay, this is called the interior angle sum theorem. So, for example, let's say I told you an interior angle of a regular polygon is 144. Now, what it means to be regular polygon is that all the sides and all the angles are the same. Meaning if all the sides are 5, if one side is 5, all of the sides are 5. If one angle is 20, all of the angles are 20 degrees. Okay? So I know all of the angles are going to be the same here. But all I tell you is that one of the interior angles is 144 degrees. So I know if there's 3 of them, they're each going to be 144 degrees. Which is going to be impossible because a triangle can't have 3 144-degree angles, right? If there's 5 of them, there's going to be 5 144-degree angles, and so forth. So I want to find the number of sides in this polygon. Well, I'm going to use this theorem that S is equal to 180 times n minus 2.
We always use 180?
Yes, the part of the theorem is that 180 goes here, right. Okay. Now, again, n stands for the number of sides, so that's what I'm going to be trying to find here is n. Okay. So I'm going to be solving for n, so I need to figure out what I plug in for s. Remember, s stands for all the angles added together, not just one of them. So I don't want to plug in 144 because 144 is just one of the angles, where this s stands for all of them added together. So in place of s, I want to plug in 144 times however many sides there are going to be. Because if it's a 5-sided figure, that means there's 5 angles. If it's a 10-sided figure, it means there's 10 angles. If it's a 20-sided figure, it means there's 20 angles. So if it's an n-sided figure, there's going to be n 144-degree angles. I just don't know what that n is yet. Does that make sense? Again, the reason I didn't plug in 144 here is because that's just one of the angles where this s stands for all of them added together. Okay. So then I want to solve this algebra problem for n. I'm going to distribute to get rid of the parentheses here. And to have 144n equals 180n minus 360. Okay, let's say I just move my n's over. So I'll subtract 180n from both sides. Okay. That gives me negative 36n equals negative 360. So when I divide both sides by negative 36, I get n to be positive 10. Again, if I would have got n to be a negative number, I probably messed up somewhere because you can't have a negative number of sides, right? So this is a 10-sided figure. It has 10 angles that are 144 degrees. The reason I know they're all the same is because it's regular. Okay, regular means all the sides are the same, all the angles are the same. Okay. And again, this is the tricky part in these, is that S stands for all the angles added together, and I had to plug in, I only gave you one angle, so I know they were n amount of 144-degree angles. There are actually 10. Okay. So now what do we name this figure? It's a what-sided figure, so what do we call it? It's a 4-sided figure, which is called a quadrilateral. Good. Okay. So it says find the measure of each of these interior angles. Okay. It's a quadrilateral. So I have a theorem that says if I know the number of sides, I can find out what all the angles add up to be. Okay. Is that if I have this theorem, I know it's a quadrilateral, so I can plug in 4 for n. 4 minus 2 is 2. 180 times 2 is 360. So again, what that S stands for is that says all the angles of a quadrilateral out to 360. Now this is for any 4-sided figure. If it's a rectangle, if it's a parallelogram like this, if it's, a square, whatever it is, any 4-sided figure, the interior angles always add up to 360. That's what that theorem tells me. The question says find the measure of each of the interior angles. So I want to know, what is angle S here? What is angle R? What is U? What is T? Okay. So I know that all of these add up to 360. That's what that theorem just told me. So I can take, let me clear out some space here. If I take 11x plus 4, angle S, plus angle T, plus angle U, plus angle R, I know all of those angles add up to 360 degrees. We actually know that because technically this is 2 triangles, right? Triangle here, each triangle adds up to 180, so 2 of them are going to have 360. But this theorem told us that already. Okay. And then I just work this algebra here. I'm going to combine what like terms I have to solve for x, and then my constants. Okay. So that's 32x plus 8 equals 360. Subtract 8 from both sides. I get 32x equals 352. Divide both sides by 32. I get 11, right? So x is 11. The problem tells me find the measure of each of the interior angles, so then I just take that x. I can go back to each of those interior angles and plug in x. So I know these two angles are going to be 55 degrees. Okay. I plug in x there. That's going to be 121 plus 4. Those are going to be 126 degrees. 126, 126, 55, 55. Oh, sorry, it's 125. Thank you. Wait, 125 degrees. So 125 in each one. Again, they should add up to 360, right? So if all four didn't add up to 360, I need to go back and check my answer. Okay. 121 plus 4, get 125 in each of these. Okay. Any questions with that? Still applying the same theorem there. All right. So this is the same problem. You don't need to write this one down because it's still a four-sided figure. I would still plug in 4 for n. They would still all add up to 360. So when I add this, plus this, plus this, plus this, it should equal 360 degrees. Solve for x, plug that in. Okay. Again, this is not a regular polygon because all the sides and angles are different. Okay. And if you did that one, you should get x is 15. Okay. Now, the other theorem, which is on your postulate sheet, is the exterior angle sum. Okay. This says if it's convex, again dealing with convex here, if it's convex, if you add all the exterior angles together, they equal 360 in every one. Doesn't matter the sides, if you add all the exterior angles together, equal 360. On the top of your postulate sheet that you can use on quizzes and tests. Okay. So in this figure, again, a pentagon, the exterior angle is formed by extending the sides. So if you added angle 1 plus 2 plus 3 plus 4 plus 5, it would be 360 degrees, always. Okay. This is a regular hexagon. Means all the angles, interior angles are the same measure, all the sides are the same measure. I want to find the interior angle and the exterior angle of this regular hexagon. There's two different ways I could do this. I could either use the interior angle formula or I could use the exterior angle formula. Okay. Again, the exterior angles we're talking about here would be like these angles. Okay. Those would be the exterior angles, so I forgot one here. Okay. There's 6 of them, 6-sided figure. There's 6 interior angles also. This one, here, here, and here. So we could first just say that these angles, these 6, we know add up to what? 360. So if I called them all x, because they're all the same since it's a regular polygon, I know 6 of the x's, so 1, 2, 3, 4, 5, 6, which equals 360. So 6x is equal to 360. Divide both sides by 6. Each of those exterior angles are 60. I just use the exterior angle theorem. Okay. This says all the exterior angles add up to 360. I had 6 of them. They added 360. Each of the exterior is 60. Once I had that, if I went through and replaced each of these angles with 60, okay. Oh, I did miss one, thank you. I know that the interior angle and the exterior angles add up to what? 180, because they're part of a straight line. They're part of the same straight line. So if that one is 60, they add up to 180. These are all going to be 120. Okay. So the answer here would be the exterior angles are 60, the interior angles are 120. Now that's one way I could have found it. I could have also used the formula we just talked about. Because I know that the number of sides in this figure is 6, so if I plug that in for n, I get 180 times 4, which is 720. Okay. Sorry, need to add. Yep. Okay. So it's 720. So then I need to find out if it's 720. There's 6 of them. I know they're all the same. If I just divide that number by 6, divide 720 by 6, you get 120. Okay. Which would have found me the interior, and then I could have found the exterior the exact same way, just the opposite. Okay. So you can kind of see how those two theorems can work together there. All right. So